So we've studied exponential models, and we found that exponential models are good things to use when we want to talk about the size of a population over time, how a population grows over time, or about the amount of bacteria in a petri dish over time. But the thing about exponential models is they're kind of limited. For example, things don't grow exponentially forever. Consider a petri dish with bacteria. We can model the amount of bacteria in the petri dish over time with an exponential model. However, the petri dish is finite, it's not infinite. So there's going to come a point when that exponential growth will not continue on. So things grow exponentially and then they take a downturn as the bacteria start to grow to the capacity that the petri dish can handle. In other words, the petri dish has what's called a carrying capacity. And as the bacteria reaches that carrying capacity, the growth slows down. Now, so we might think so we might think consider this thing. Let's suppose that we've got the amount of bacteria on the vertical axis and time on the horizontal. We might see a situation like this, where we have growth that follows this typical exponential pattern, and then it kind of tapers off and takes a downturn. And that downturn involves, when that downturn happens, uh, involves the carrying capacity. So the petri dish has a certain amount of bacteria that it can have, and as the amount of bacteria grow toward that, the growth rate slows down. So this right here, this uh, this horizontal asymptote here is the carrying capacity. Now, because of this fact, because of this truth, we don't always model things just with a straight out exponential, a to the x power or a to the t power. Instead, we have this thing called a logistics curve, a logistics model. And I want to explain. I think I'll explain this with an example. Let's suppose that there is a college campus with 5,000 students, and let's suppose that after break, one of the students comes back with a virus. Now, this is a situation where we might want to use a logistics model to model how many people are going to have the virus over time. And without getting in the details where this model comes from, let me just write down, a model that might describe this. Let's suppose we have f of t equals, let's see here, there's 5,000 people on campus, and down on the bottom we would have 1 plus 4,999 e to the negative zero point 0.8 t. This is, this is just a typical logistics model. And we're not going to worry now where I got these numbers, except this number up top, this 5,000. Notice that is the number of students on the campus, and there's never going to be more than that many students with the virus. And think about this model, how it looks. If t goes on, in other words, as time goes on, notice this 4,999 divided by, notice this is a negative exponent. This term right here goes to 0 as t goes to infinity. So what you end up with as time goes on, the number of cases approaches 5,000. And this 5,000 right here, this is the carrying capacity. That's what that 5,000 is. So if you're given a logistics model and you are asked, well, what is the carrying capacity? You would find it right up here, 5,000. Now let's look at what this would look like graphically. Okay, so I went ahead and entered the logistics model right here, and I adjusted my window. Notice I came over here and I went to this little wrench, and notice the y goes from 0 to 7,000. Because the carrying capacity is 5,000, I wanted to be sure I captured that part. And then I just set the x from 0 to 22, like that. Now, so this is what the curve looks like. Now, I'm going to put down here the carrying capacity. So y equals 5,000, just so that we can look at that graph. There it goes. And I guess maybe I can change this to, just stand out a little bit, change the color, make it a broken line. So there is the carrying capacity, and notice it goes right through the 5,000. Now, let's suppose that this school has this policy that they're going to close the campus if 40% of the student body is infected by this virus. Well, let's see here. So we need to calculate 40. So we want to know how many days is that going to take. X is in days, let's say. Well, 40% of 5,000. Well, 10% is 500. 4 times that is 2,000. So let's do y equals 2,000. There. Right there. This is where these two curves intersect. That's when 40% of the population of the school is infected. In other words, when 2,000 students. So let's just click on that and see when it is. It's in about 10.139 days. That's when 2,000 of the students will be infected. Now, let's suppose that we want to change this model a little bit. In other words, let's suppose we would like to spread this out a little bit. And maybe we're desiring that we could go at least 20 days without having to close campus. Well, the way we could spread this out a little bit is we could change this number right here. Now, let me do this down here. I have 5,000 divided by 1 plus the same thing. I'm going to enter the same thing, except it's going to be e to the, let's say, negative point, let's say 7x. Look at this. We did have the number occurring here when 2,000 will be infected. Now it's occurring over here, day 11. So maybe we could change this a little bit more, maybe 0.5. Now look at out here. It's 16 days. Maybe make it 0.3. Now it's quite a bit of ways out there. Let's see. 27 days. So you notice this number right here affects the steepness of the graph. So with this model up here, this f of x, it took 10 days. With this model down here, I guess I'll call it g of x, it took 27 days. Okay? So if you're asked, well, what could you change about the model so that 40% of the students aren't infected until like day 27 or something like that? Well, what you do is you play with this number down here. So maybe what would happen is, let's suppose they want to make school last at least 27 days instead of this 10 days. Well, they know they need this to be negative. They know they need this to be 0.3 down here. So they might look at ways to make that happen. Maybe say, okay, if we make all the students wear masks, if we encourage them to social distance, if we, have more remote classes where the students can stay in their dorms for classes. In other words, if we limit interaction, maybe we could get it down to 0.3. So this is an example of a logistics model. Now notice the top number gives you the carrying capacity, and the bottom right here, this exponent of the e gives you the steepness.